Welcome to our course project assignment presentation for ANA675, Neural Networks and Deep Learning at National University. We are Group 1, Joseph Allibone, Veer Fonbon, and Ron Darnell. We compared two approaches, a classical machine model and the support vector machine, and a deep learning model, the convolutional neural network. Our task was to classify grayscale images of clothing into 10 different fashion categories. The goal is to explore how model architecture affects performance, accuracy, and overall efficiency. The primary goal of this project is to compare and evaluate two different machine learning approaches for solving the same classification task. First, we wanted to explore how a traditional machine learning model like support vector machine, SVM, performs when given image data that has been flattened into vectors. Second, we wanted to assess how a deep learning model, specifically CNN, handles the same task using full spatial structure of the images. Our project objectives include model building, designing an SVM and CNN architecture suitable for this dataset, training and tuning, optimizing hyperparameters to get the best possible performance from both models, evaluation, measuring performance using metrics like test accuracy, misclassification counts, confusion matrices, and validation accuracy trends. In comparison, analyzing the differences between the two models, not just in accuracy, but also in training time, stability, and ability to generalize to new data. Ultimately, the project helps highlight why deep learning models like CNN are preferred over image data, but also show that simpler methods like SVMs have value, especially in lower resource or simpler classification tasks. We use the Fashion-MNIST dataset, a popular benchmark dataset for image classification. It contains 70,000 labeled grayscale images of clothing, each sized at 28 by 28 pixels. It's divided into 6,000 training images and 10,000 testing images. Each image belongs to one of 10 fashion categories. The 10 classes shown on the slide are t-shirt, trouser, pullover, dress, coat, sandal, shirt, sneaker, bag, and ankle boot. The Fashion-MNIST provides a non-trivial image classification task, making it ideal for evaluating traditional and deep learning approaches. The inputs are 28 by 28 grayscale images of clothing, and the output is one of 10 fashion categories, sneakers, coats, or shirts. Here you can see a sample of the data set showcasing the different classes. Support vector machines, or SVMs, are a type of supervised machine learning algorithm primarily used for classification tasks. The core idea behind them is to find optimal hyperplane, a decision boundary that best separates the different classes in the feature space. In 2 dimensions, this hyperplane is simply a line, but in higher dimensions, it becomes a plane or a hyperplane. What makes SVMs powerful is that they do not only try to separate classes, but maximize the margin, the distance between the hyperplane and the nearest points from each class. A larger margin typically means a better generalization and robustness. Advantages of SVMs is that they are very effective when the data is clearly separable and perform well with smaller data sets. They are relatively quick to train compared to deep learning models and can use different kernels to handle nonlinear data. Limitations for images in these models: to use SVMs with images like the Fashion-MNIST, we must flatten the 2D pixel grids into 1D vectors. This flattening loses important spatial relationships like edges and patterns that are critical for visual understanding. As a result, SVMs often struggle with tasks that require recognizing complex spatial structures, such as image classification. This limitation is one of the main reasons deep learning models, like the convolutional neural network, CNNs, outperform SVMs for image-based tasks. There is no specific architecture diagram for the SVM because SVMs aren't neural networks and don't have a multi-layer architecture like CNNs. Instead, for SVM, we describe the support vector machine model operates on a flattened image vectors. Each image is flattened into a feature vector. Hyperparameters like the kernel are selected through grid search, and SVM algorithm is trained to separate classes. The trained model predicts the clothing category for new images. Each 28 by 28 pixel grayscale image is reshaped into a 784 dimensional feature vector. Grid search CV was used to optimize two hyperparameters, the kernel function, linear or RBF, and the regulation parameter C. So we can describe the architecture as start, flatten image, 28 by 28 image to 784 features, choose the kernel, linear or RBF, then train the SVM model and predict the fashion category. To improve the performance of our SVM model, we conducted hyperparameter tuning using grid search CV. During hyperparameter tuning with grid search CV, we evaluated multiple combinations of kernels and regulations, parameters, or C values. Our best performing configuration achieved a mean cross-validation accuracy of approximately 87%. This means that across different training validation splits, the model consistently generalized well to unseen data during tuning. Choosing the RBF kernel with a moderate C value proved optimal for balancing model complexity and overfitting. This strong cross-validation score gave us confidence that the SVM model would perform reliably on the test set. The RBF kernel with C equal 10 provide the highest validation accuracy of approximately 87%, showing that flexible nonlinear boundary was better suited for the complexity of the Fashion-MNIST than a simple line separator. Our tuned SVM model achieved 78% accuracy on the dataset. Out of 10,000 test images, approximately 8,667 were classified correctly, leaving 1,333 misclassified. Precision, recall, and F scores averaged 80.87, suggesting balanced performance across the classes. We observed that simple distinctive items like trousers and sneakers were classified accurately, while confusing categories like shirt versus coat posed greater challenges. The confusion matrix reveals the model's strengths and weaknesses. The SVM easily recognizes items like trousers and sneakers. However, there is much confusion between shirts, t-shirts, pullovers, and coats. Since the SVM treats images as flat vectors rather than preserving spatial structure, subtle differences in clothing style are harder for the model to distinguish. Convolutional neural networks, or CNNs, are a class of deep learning models specifically designed for image data. CNNs are designed to exploit the spatial structure in image data. Unlike SVMs, CNNs preserve the spatial structure of images by using convolutional and pooling layers. This allows them to detect patterns like edges, shapes, and textures effectively. Layers like convolution and pooling allow the model to detect patterns and features automatically. CNNs are better suited for image tasks compared to flat feature methods like SVMs. CNNs do not flatten images and retain spatial locality, making them far more effective for visual recognition tasks. We designed a relatively simple CNN with two convolutional layers, each followed by max pooling. This slide presents the architecture of the convolutional neural network, or CNN model we used for the dataset. Classification task. The model begins with a conv 2D layer that extracts local features from the input images using 32 filters. After convolution, a max pooling 2D layer reduces the spatial dimensions, helping to make the model more efficient and less sensitive to minor shifts in the input. A batch normalization layer is applied to stabilize and speed up the training. Next, a second conv 2D layer with 64 filters further extracts complex features, following again by max pooling to compress the feature maps. The output is then flattened into one-dimensional vector, connecting it to two dense layers, fully connected layers. The first dense layer has 128 neurons and applies a dropout layer for regularization to prevent overfitting. Finally, the last dense layer has 10 output neurons corresponding to the 10 fashion categories. Using a softmax activation to output class probabilities, the overall model contains about 225,000 trainable parameters, striking a balance between model complexity and training efficiency. During training, we also implemented early stopping. Early stopping monitors the model's validation accuracy during each epoch. If the validation accuracy doesn't improve over a few consecutive epochs, in our case it was 3, the training model automatically stops. This technique prevents the model from overfitting on the training data while also saving time and computational resources by not running unnecessary additional epochs. To train our convolutional neural network, we first pre-process the Fashion-MNIST images by scaling the pixel values between 0 and 1 and reshaping them into 28 by 28 by 1 tensors to preserve spatial structure. The CNN architecture consisted of 2 sets of convolutional and max pooling layers, followed by a flattening operation and 2 fully connected dense layers. We used the ReLU activation function in hidden layers to introduce non-linearity and a softmax in the final output layer for multi-class classification. We trained the model using the Atom optimizer with categorical cross entropy at the loss function appropriate for multi-class problems. To avoid overfitting and reduce unnecessary time, we applied early stopping callback. As shown in the training history plot, the model reached its best validation accuracy within 6 epochs. The validation and training accuracy curves remain close, indicating stable learning without significant overfitting. This graph shows the training and validation accuracy trends over epochs for the CNN model, and as you can see, training accuracy kept improving steadily until it achieves the best validation accuracy at approximately 91%. However, validation accuracy plateaued around the 3rd to 4th epoch and then slightly declined after that. Thanks to early stopping training, the processing training was automatically halted once the model's validation performance stopped improving. Here we see the CNN model results. After training for 6 epochs with early stopping, the model achieved 90.3% accuracy. Out of 10,000 test images, it made about 9,030 correct predictions and 970 misclassifications. The model performed exceptionally well on easily distinguishable classes like trousers, sandals, bags, and sneakers. The biggest confusion was the shirt category, which makes sense because shirts can visually resemble t-shirts, dresses in grayscale. Overall, the CNN distributed excellent spatial feature extraction, significantly outperforming the SVM, especially on more visually subtle classes. Here we analyzed the CNN confusion matrix. We observed high true positive rates for several classes. For instance, trousers, sandals, sneakers, and bags are all classified correctly over 97% of the time. CNN significantly reduces misclassification compared to SVM, especially for visually distinct items. The majority of the remaining errors involve confusing shirts with t-shirts, pullovers, or coats, which is understandable because these categories are visually similar. The CNN's ability to preserve spatial information allows it to outperform SVM image classification task. This slide summarizes the side-by-side performance of the SVM and CNN models. First, looking at test accuracy, the CNN achieved significantly higher score of 90.3% compared to 86.7% for the SVM. This highlights CNN's ability to leverage the spatial structure of image data for more accurate predictions. Training time was relatively close. The SVM model trained at about 62.5 seconds, while the SVM completed training in 68.1 seconds. Despite the slightly longer training, CNN delivers noticeably better classification performance. The SVM incorrectly classified 1,333 samples. When considering misclassification, while the CNN had only 970 misclassification, This reduction error further demonstrates the CNN's strength. Lastly, that note while the SVM doesn't use validation to set optimization in its training directly, the CNN achieved the best validation accuracy of 91.1, indicating good generalization to unseen data. Overall, the SVM is faster and simpler. The CNN clearly offers superior performance, especially for tasks involving image data. In this project, we compared two different modeling approaches for image classification: support vector machines, SVM, and convolutional neural networks, CNN. The SVM, a traditional machine learning model, performed reasonably well with 86.7% accuracy, but it flattened in the image data and lost important spatial information. The CNN, designed to preserve spatial structure, achieved a higher 90.3% test accuracy and demonstrated fewer misclassifications, proving its advantage for visual tasks like the Fashion-MNIST dataset. Training times were comparable, but CNN's ability to learn hierarchical patterns like edge textures and shapes made it more effective. So in conclusion, CNNs are better suited for complex image recognition tasks because they remain spatial features. SVMs can still serve as useful baselines for simple structured data. Understanding model architecture and data structure is critical for selecting the right machine learning technique. This comparison highlights how important model selection is based on the problem type and why deep learning often outperforms classical techniques for visual data. This is the list of references that we used during our project, and thank you.